Welcome, ladies and gentlemen, to the shape of the universe. Let me start by asking, does anybody already know the shape of the universe? I asked my friend and he said, it's donut shaped. And I thought, wow. And then he said, with jam in the middle. We're going to be very interested in what the centre of the universe is, finding out about the centre of the universe tonight. But let's crack on and get started with the serious side of it. In order to set the scene a little bit, let me ask, why does the shape of the universe matter? Well, part of it is the fun of being able to say to people who are perhaps oversure about what they know that actually that might not be correct. There might be other ways, there might be other factors that have not been taken into account that directly contradict what otherwise appears to be so certain. So there's fun to be had in that. There's fun to be had in saying, I don't care how certain you are, I think you're wrong. So I hope that as we're talking about this, you'll be not only understanding what I'm saying, but also feeling confident enough about that understanding that you can actually share that yourself with other people and put it into your own words. That's the level of understanding I'm hoping that you'll come away with. That's one reason why you might be interested in the shape of the universe. Another reason why you might be interested in the shape of the universe is that physics currently has a number of pieces of the jigsaw that don't fit together. The shape of the universe is the picture on top of the box. It's not just the edge pieces, it's the whole picture. So we'll see as we go through, I think, how important it is to have an overall picture that things can fit into. And if something doesn't fit, then that overall picture is somehow wrong. But people who have a vested interest in some aspect of this material are completely free to take away these ideas, reframe them, repurpose them, put them into your own words, publish and copyright. Absolutely no problems. I get paid for giving the talks, but the material and the work I've already done, I'm not expecting to get paid for. Let's see what's involved tonight. Okay, so we've got a series of steps to go through. There are 3 parts, as you can see here, and there are a total overall of this number of steps. So I'm not blinding you with science, I'm not blinding you with wild animations. It's a very straightforward limited set of steps that we have to go through that will take about an hour and a quarter, hour and a half, depending on what questions you might have. And if you do have questions, by all means ask them as we go through. That's part of the reason for having not too big an audience, so that we can make sure that we're all on the same page as we go through. There is a money-back offer. The money-back offer is not on the basis of you don't agree with me. It's not on the basis that you don't like the show. The money-back offer is solely on one basis, which is that if a member of the audience sees or hears something that is factually incorrect, then at some point they can raise that. If they can convince a majority of the audience that what's been said here is factually incorrect, then the whole audience gets its money back And frankly, it's back to the drawing board for us. So we would not be able to continue with doing these shows. Assuming that doesn't happen, then we'll have a vote to see how persuaded people are, the majority of people are, by what's been presented as the answer to the shape of the universe. And then we've got a little bit of conjecture about some things that are less certain. So we start off with what the shape of the universe isn't, to get us all on the same page. We move on to what the shape of the universe is, and then we move on to what that means in terms of the practical effects. Straight in, the shape of the universe isn't. Now, when I was at school, this is what I was taught. There's a universal set, which is basically an oblong because it's shapeless. And there's a set of infinity that might be in the universe, or might be all of the universe, or perhaps there's more to the universe than just the universe, if you see what I mean. So, here we can ask the question. Here we can clearly ask the question, what is outside the universe? If you go outside of the box or outside of the set, what is there? What is this? What does nothing look like if nothing is outside the universe? So behind this we have a Mandelbrot set. You may recognise this. And a Mandelbrot set is interesting because it has an infinite perimeter. And the typical example is the seashore. That's surprisingly applicable to the edge of the universe. A Mandelbrot set has effectively an infinite perimeter. So any Mandelbrot set any fractal in fact, will have this feature that you never get to the edge of it because you never get to the end of it. The New Scientist published this news item on its website in 2008. Galaxy map hints at fractal universe. Is the matter in the universe arranged in a fractal pattern? A new study of nearly 1 million galaxies suggests it is, though there are no well-accounted theories to explain why that would be. Now, a Mandelbrot set is a mathematical idea, but what we appear to be being asked to consider is that the universe is fractal on the largest possible scale, and that's where the edge is. And if you go as far as it's possible to go, you will only reach these larger and larger structures. You will only ever see an increase in what is in front of you. So therefore you can never get beyond the edge of the universe, because it simply goes on forever and ever and ever, getting larger and larger and larger. That begs a bit of a question, which we've touched upon already. Excuse me. Where then is the centre of the universe? Well, we've had an insight into the shape of the universe, mathematically speaking, for some time, because Blaise Pascal originally said the universe is a place whose edge is nowhere and whose centre is everywhere. We can see what he meant. I mean, that's a breathtaking insight to have when you don't know about expanding universes and fractals and so on and so forth. It's astounding to me. And see what he means when he talks about the edge being nowhere. When he talks about the centre being everywhere, that's even more interesting for a different reason, because if you think about two entangled particles, then really they're kind of behaving as if they were the same particle, or more, two or more entangled particles. It doesn't matter how far apart they behave as if they were the same thing. And it's as if they are somehow at the centre of the universe because they are so small. So in the same way, or in the opposite way, that the edge of the universe is exponentially big, the centre of the universe is exponentially small, but it is everywhere. So it's kind of difficult to visualise, but mathematically speaking, that would be where we would be ending up when we think about the shape of the universe mathematically in modern terms. Putting that into a picture, we still have a set, but we have a uniform set with a blurred edge and what might be infinitely small, but is still an infinite centre. Now there's a conclusion that we can reach at this point, which is that Georg Cantor and his ideas of multiple levels of infinity is ugly, clunky, and ungainly. I'm a computer programmer, and one of the things that any computer programmer will tell you is that we know when our programs have a bug because they don't finish, they don't complete their execution. What happens is you miss off a condition or a check, or you just plain write it wrong, incorrectly, and the program goes into a loop which it will never come out from. So you have to break into the program, and then you have to work out where your bug is in the program. Cantor's proof of multiple infinities tried to do exactly that. It tried to say, well look, if you line up all the integers, 1, 2, 3, 4, 5, against the real numbers, 1.1, 1.12, 1.13, blah blah blah, then you will find there are more real numbers than there are integers. Which might have been true if it was ever possible to do that, but it's never ever going to be possible to line up all the integers. So it's a completely meaningless comparison, and it's a broken algorithm. It's not a mathematical proof, it's a broken algorithm. So Cantor is one of the people who is a victim of this mathematical shape for the universe, which has a name. It's called the transfinite set. Basically, we're saying that the edge, even though it's going on forever and ever, getting bigger and bigger and bigger, actually the word for that we need to start using is infinitesimal. We always think of infinitesimal as being small, but its size is nothing to do with anything that's infinite. If you think about it, if you think about, for instance, pi, if you think about the decimal expansion of pi, that goes on forever and ever and ever, and it never repeats. The decimal expansion, each digit of that is a maximum of 9/10 of the previous digit. So that is, quotes, getting smaller and smaller and smaller as it goes on. However, at the same time as it's getting smaller and smaller and smaller, it's getting longer and longer and longer. So it's getting bigger and bigger and bigger. So it's not correct to think of anything that is infinite in terms of size. And that means that Marcus de Soto, writing in The Guardian in 2009, is also a victim of our shape of the universe, because he says the smart kids will go for infinity as the largest number imaginable. It's completely not the case. Infinity is not remotely like a number and doesn't have any size, and all infinities are the same infinity simply by Occam's razor. We talked about the shape the universe isn't mathematically. What about the shape the universe isn't physically? We've got a shape here which is from NASA. Who wants to tell their friends that NASA is wrong? This is your chance. This shape shows a period of super fast inflation really early on in the universe, and then a steady expansion which apparently is accelerating later on. There's nothing here about the universe being 43 billion light years across, so I'm not totally sure what this represents. It is trying to say that it's 13.7 billion years old across the longitudinal axis, but I'm not sure what it would say about this width. It perhaps thinks, well, it's not proven in some way, this figure of 96 billion light years, but I don't know. I don't want to convince you I'm right and everybody else is wrong in what I'm about to say. What I really want to do is I want to try and give you doubt about this. I want to give you doubt about NASA. We're not going to decide what the shape of the universe is tonight. We're not going to decide it this week or next week or even perhaps this year. That's for due consideration in the cold light of day by the majority of experts. All we're going to do is we're going to try and build our own understanding for our own pleasure tonight. And I'm hoping that it will be a pleasurable thing for you to understand. By doing so, you will also be sharing with me a certain amount of cognitive dissonance, because one thing that's sure is that when we leave here, people are still going to be saying, oh, this must be right because it's NASA. People are still going to be saying, dark energy, dark matter, they must be right because everybody thinks they are. So there's a certain uncomfortableness in having advanced knowledge about these elements. But that's the least of our worries, I suggest, overall. Now, I want to talk a little bit about the Big Bang now, so that I can explain the alternatives to this, and the particular alternative I like. So, typically the Big Bang is treated or looked at or imagined as if it was either an expanding balloon or, rather than a popping balloon, perhaps a firework that explodes into a bunch of beautiful stars, and then that's the firework spent. I want to persuade you that's oversimplified, massively oversimplified. In actual fact, it's much better, much more effective, much more valuable to think of the shape of the universe and the Big Bang, the expansion of the universe, as being like a gong. Instead of the Big Bang, because it's nothing to do with size, as we've already discussed, it should be called the long bang, or better still, the long bong, because it was from a gong. Anyway, I won't dwell too much on that. Now this is where I'm going. So I'm coming from a situation of numbers, and I'm going to do that with the aid of two things: a frog and, oh yes, money. This is my table. This is the size of the universe, and I've got two columns. This is the expansion rate of the universe, and I've got two extra columns that most people wouldn't have and aren't in the previous diagram. I've got the apparent size of the universe, not the real size, just what appears to be the size. And I've also got the expansion of the universe on a compound basis, not on a simple balloon-based or firework-based basis. Here's where we get to money, because with money you have simple interest and you have compound interest. Now bear with me, because we have to kind of go into metaphor for me to make sense of this, but you will see why I'm saying this. Let's imagine I'm seeking to open an account with the Bank of England. The Bank of England suddenly starts allowing ordinary people to have bank accounts, and the reason why I want to have a bank account with the Bank of England, apart from all of the nice reasons, is because they're offering 100% interest. Fantastic. 100% interest, I can put in £1, it'll receive 100% in the first year. Great, I've got £2. If I leave it in 100% in the second year, I've got £4. Leave it in £8, 16, 32, so on and so forth. There's one problem there for both myself and Bank of England, and that is an exponential rate of growth. At some point, I am getting paid so much in interest that the Bank of England is in debt to me. And the more customers that take up this offer and put their money in the bank, the quicker the bank becomes indebted to all these customers to an extent it can't pay, or won't pay, which is just as much of a problem. So I'm going to say to the bank, look, that's great for me, but it's not great for you, and because it's not great for you, I can't take advantage of it. I can't buy in. I can't buy into it. So what do we do? What is the solution? Here's a possible solution. The Bank of England says, okay, what we'll do is we'll pay you a falling rate of interest, so that instead of it being an exponential geometric progression, it becomes a manageable arithmetic progression, so that we can benefit, we can all benefit. How do we do that? I'm going to put in my capital of £1, and I'm going to have along the top years, year 3, year 4, year 5, etc. Now my interest starts off at 100%. So I put in £1. I'm going to change this slightly. I'm going to make that year 0. 1, 2, 3, 4. And I'm going to say the interest is payable in year 1. So it's at this point I get £1. I've still got my capital, so I've got a total of £2. Simple enough. In year 3, the interest halves. It drops to 50%. Instead of And this is on the capital that I've got. Remember, the capital is going to basically be this amount forever in this scenario. The interest is going to be £1 each period. So this is going to go £2, £3, £4. The interest 50% is 50% of £1, so that is interest of 50p, which becomes £1, which becomes £1.50, and so on and so forth. So, along here, our progression becomes £1, £2, don't know what that means, £3.50. At this point, we've got to add in the 25 pence. I'll fill in this one as well, so that becomes 50, and then this becomes 12.5 pence. So we've got 3, 4, 5, £5.25, and so on and so forth. Notice that those numbers along there, £1, £2, £2, £3.50, £5.25, are what I have said is the real size of the universe as a result of its expansion. 1, 2, 3.5, 5.25, 7.125. Although the universe is expanding, it is not an explosion with an exponential increase in its expansion. It's not a balloon with a steady increase in its expansion. It's an accelerating expansion, and that's the most important thing about this. It's not a runaway expansion, but it is an accelerating expansion, because as we'll see later, I don't want to jump the gun at all, but I think I kind of have to at this point. Acceleration is gravity. So if it's a big if, but I think it's the only possible one worth talking about. If the universe is expanding on an accelerating basis, then it has additional gravity. So this is the sequence that corresponds to the size of the universe as a result of this compounded expansion. So the expansion became 100% at this point, it became 150% at this point, it became 175% at this point, and that's what we've got here. 175, 1.875, 1.9. And what's interesting about this, as you can see, is that it pretty quickly tends towards a limit. And the limit is 2. So, although this looks great at the start, it very quickly falls away to become really not significant amounts. Ultimately, you're adding 1 plus 1 at the limit of this projection. And that's what we're seeing here. And that's what we're seeing here as well. As the universe gets older, the expansion relative to the start is a maximum of 2 units of what it started out as. So when people say 96% of the mass is missing, what they're really saying is, if we were to assume that the expansion rate was this fixed value all the time, which is what NASA's diagram is saying, with a little bit of expansion added on, then we would And if you add all these up and look at it as a percentage of this, you'll find it's a lot more than 96%, it's about 99%. The mass isn't missing. And if we have time, I'll talk about the frog, and I'll talk about where this apparent size for the universe comes from, and we'll talk about how we derive this 93 billion light years, or get close to deriving this 93 billion light years. I'm conscious that I've had to spend a bit of time going into this, so we're moving on to the second part of the presentation now, where we discuss the actual shape of the universe. And in a way, I'm taking us back to 2004 or so, which is when I first started thinking about trying to visualise the shape of the universe. I've got some 3D software, so I was trying to visualise it so that I could use this software to model it. And I ended up imagining this sort of infinite singularity at the centre, surrounded by this blurred border around it. But because it's the same infinity, I was linking them at first on both sides, but then really only on one side. So the donut shape I started off with, I cut the bottom half of it, cut the half off of it, and I ended up with this like funnel shape that looked like this. Lo and behold, 2004, I saw this on the New Scientist website, the Picard topology. And this, as the headline says, looks like a medieval horn, and although that doesn't sound plausible, according to Frank Steiner at the University of Ulm in Germany, recent observations hint that the cosmos is stretched out into a long funnel with a narrow tube at one end. So this is as a result of measuring the local space and extrapolation. So it's a physical measurement. What we've got then is a shape for the topology of the universe. It's a shape that isn't three-dimensional. In other words, there isn't anything in the funnel. Although there's nothing in the topology represented here, I'm still holding on to an infinite singularity at the bottom, so I've got a dot to represent that. In terms of the expansion of the universe that we've been discussing, this business about something that isn't an explosion but is more like a continuous sound, a vibration almost. The expansion causes the top to grow. Similarly, it causes the bottom to shrink. So rather than this getting longer and longer and longer, actually this is getting shorter and shorter and shorter, except that because it's infinite, there's no background to measure the shrinkage against, so there's no way to tell applying the topology. As I've said, acceleration is gravity. It's not just the case that, as Einstein said, when you're a person in a lift who cannot see outside, feels the acceleration of the lift the same as if he was actually standing on a surface with gravity. He can't tell the difference, in other words, without being able to see the background and see that he's accelerating. Now, when we look at a series of galaxies, we're missing the fact that they seem to be hanging there in space. We're missing the fact that these are moving. I've replaced galaxies with cars, so it's extremely apparent that these are accelerating as a result of the acceleration from the long bong earlier in time. in actual fact, these cars are not flat and all going in the same direction. They're all going in completely arbitrary different directions, including across each other and colliding with each other. And they're not coming out from a centre. There is no centre to come out from. They're as much likely to crash into each other as they are to move away from each other. This means that there's no need for any dark energy or dark matter, because it's all just acceleration from the expansion of the universe. And the reason why scientists don't know this is because they're looking at, effectively, by looking at the universe over this tiny time frame that humans have been able to look at. It's like looking at a still from a film and trying to work out what the film is. That's the real analogy, when the shape of the universe isn't so much the picture on top of the box as it is the film strip that makes sense of the individual snapshots. This business of acceleration has a very practical effect, which we can apply in our own case. Let me give you 3 examples of a single scenario. The first example is where we have a black hole that is outside of a set of stars that are gravitationally linked. And this black hole is approaching on a collision course. Now, if the black hole is moving very fast, or is very heavy and therefore has a lot of impetus, it might strike a glancing blow on this group of stars and then push on and push through and escape. That's scenario 1. The black hole is not captured, but it does impel the group of stars, rearrange them, and it does continue onwards and is only partially gravitationally affected itself. Scenario 2, a lighter, slower black hole is approaching this group of stars, and this time the group of stars arranges themselves around the black hole, and the whole thing continues on its way as a single group. So that's scenario 2, where the black hole is fully captured as a result of its path into and through the stars, this group of stars. Neither of those is the situation that applies to us, i.e. with the Milky Way. In this scenario, we have a third possibility, which is that the black hole is of a particular weight or speed that causes it to reach our group and then push on through, but our group arranges itself behind the black hole as it pushes through. And so this group of stars, which is gravitationally linked, just like it was in the other 2 scenarios, is actually going to have a slowing effect on this black hole, just as this black hole has a sucking effect on the group of stars. So it will end up, well, how will it end up? In this diagram, we have a Mexican hat behind the 3 scenarios. The reason being that, as we probably all know, the Mexican hat is the typical model for the gravitational field of a body. And I got, well, the closest I could get to a Mexican hat was this. It's actually an egg poacher, so you have to use your imaginations, but what we're saying is that if we imagine the black hole is in the bottom of the cup, then what we're saying is that the stars pulling back on the black hole have the effect of squashing the top of the Mexican hat, like this. So what happens then? Well, even though these stars that are gravitationally linked are not solid, it's more like a thick jelly than it is a solid. I think the same thing happens as if it was solid, which is that this cup actually tears as a result of the downward pressure. So what happens is you get these arms coming out, and because the whole thing is rotating around, the arms actually curve, and so you get the spiral arms of the Milky Way and a typical spiral galaxy. Now, unfortunately, the eggs that are getting broken in making this particular omelette are the eggs of faster than light travel, warp drive. The scenario that we have imagined as our future, from Star Wars to Star Trek, is really questioned with this shape of the universe, because the fact that it's been accelerating and so extremely early on has created these vast distances that we simply cannot expect to cover, except with an unimaginably difficult amount of work. The idea that we're going to be able to get on a spaceship and somehow magically go anywhere we want is dead, and perhaps not before time, because, in my opinion, and I've read a lot of science fiction, in my opinion, the faster than light idea is actually less attractive than no faster than light. So much so that I've made a video about this as well online. The main reason why is because if you think about the vastness of the universe, being able to go somewhere instantly or almost instantly, where would you go, and what possible reason could you have to stay there? Really, if there was such a thing as this warp drive, the only reason to stay anywhere would have gone. There'd be no... We're already treating our Earth like it's disposable, which is totally counterproductive. We're doing that because we're encouraged to by this idea, this dream of cracking the mystery of the universe. Well, really, we need to somewhat have a more adult dream than, unfortunately, we do at the moment. And part of that is realising, well, actually, it does make more sense if the universe has a purpose. For example, we're not going to be able to come back from wherever we go in the universe. It's going to be a one-way pilgrimage. It's not going to be to and fro. Because of entanglement, it's likely that we'll have instantaneous communications, which is terrific. It'll mean that we're still connected, we're still human, even though we're going to diverge, we'll still essentially retain the core humanity. Where are we going to go? Well, there's only one place to go, and that's into the centre. We've got to be looking at going into the Milky Way galaxy and exploring that, not anywhere else. There's nowhere else to go, nowhere at all. And we're looking at a vastly longer time scale than we normally imagine. It's it's so difficult to get into space. It is going to take all of us. It's going to take the lowliest, meanest, dirtiest, least appealing of us to contribute to this, to make it happen. Because you cannot afford to assume that all we need is another Einstein and we'll all zip off. That's simply not credible at all. So I think the film I've made is very interesting. It basically says, well, hang on a minute. Suppose you say it's not going to take us the invention of warp drive and minutes or hours to get to the centre of the Milky Way. It's going to take the same amount of time to get to the centre of the Milky Way as it did to get here on Earth. That's 4 billion years of evolution on Earth. So how about having a look at the possibility of 4 billion years to get to the centre of the Milky Way? And that's what I found so interesting. So that's what this film that I made is about, and that's available on YouTube. So please do have a look. I should say that there's a book available that goes into this in a lot more detail in terms of the effect of gravity in specific situations which are of interest to us. So this is a very short essay which is available free of charge online, or you can buy a print copy like this for just £8.25. You'll see it's quite nice, it's in full colour with illustrations. And you can get that from lulu.com, sent directly to your home address. Well, we've reached the point. I've covered everything that I wanted to say, so thank you so much for letting me go through all that and your patience. We are at about an hour and a quarter in, so that's great. We've covered everything except the green column from my table of figures, which we can go back to if people are interested in due course. But now's the time to take the vote. Beforehand, if you've got any questions, anything you want to ask, now's the time if you haven't already asked it. So I'll give you a couple of minutes to think about it, then I'll come back, take any questions, and then we can see it. We can see what the consensus is amongst tonight's group. Finally then, let's push on a little bit from the ball, from, if you like, the bare facts, into area of perhaps greater uncertainty, but also equally additional interest. We've dispensed with dark energy, we've dispensed with dark matter. We've said that because of the expansion of the universe is accelerating, the acceleration is what creates extra gravity and what creates a history of gravity previously, and so there is no further explanation needed for us. What about this third weird phenomenon of dark flow? I'm glad you asked. We've got at the centre of our universe a singularity which is also separate from the universe. The singularity is pushing towards the universe. You could say that the universe is pushing towards the singularity. You could say the universe wants to be close to God. You could say that. And you could also say, going back to our picture of a transfinite set, you could also say that God at the centre of the universe is the final state of the universe. It's not necessarily the state of the universe now. The state of the universe now might be an arbitrarily off-centre God, because You don't fix the universe overnight. The one thing we constantly see is that the universe has purpose. It has so much purpose that there's a point to it being off-centre. This is a New Scientist article from, again, 2009. Sasha Kashlinsky at NASA has found a group of galaxy clusters moving at an extraordinary speed towards a small patch of sky between two constellations, which they call dark flow. There's no obvious reason why the clusters should be moving at such breakneck speeds. But it's as if this is the point, an arbitrary point where everything is falling even faster into the centre than all the rest of the universe. In terms of what I'm saying to you, which is that I believe that we have all the answers, not just to the shape of the universe, but also to our questions about how gravity works in cosmology, why there seem to be these discrepancies, including this business about 96% of the matter missing, the universe being 13.8 billion years old but only 93 billion light years wide. All of these things I think we can now assign true or false to and be pretty confident that we have a solid working assumption from which to proceed. So why don't physicists know this? Well, I do wonder about the question, and sometimes I get maybe a little bit glimmer of insight. So, for instance, one example is scientists, physicists and mathematicians are very interested and concerned with the number of dimensions that the universe has. We're constantly told that space-time is a four-dimensional construct, where it's suggested to us that perhaps through string theory or some such confection, there may be 7 dimensions or 11 dimensions or however many dimensions to the universe. I think that is getting hung up on something that simply is a blind alley, a complete dead end. The universe is infinite, there's absolutely no doubt about that. And how many dimensions does an infinite universe have? Well, it has an infinite number of dimensions, which is why 3 dimensions is still far and away the best possible approximation to an infinite universe. Even 4 dimensions isn't a better approximation. A more fruitful question to ask might be, but which 3 dimensions? And that's actually how I got into this whole shape of the universe business. It's because before I even started thinking, it's because well before 2004, I was writing a book about the definition of the human mind. And this is it. It's much longer than the physics book, and much more comprehensive, and I'm trying to write a sequel to it at the moment. And the suggestion I'm working on would mean that there were still 3 dimensions to space, but, and here's the shocker, they're not objective dimensions. You have to bite the bullet and realise that we cannot proceed forward by simply demanding that the universe obey our desire to have objective dimensions, because it's not going to happen. What do I mean by that? Well, here's a picture of what I mean, which is that space, having a topology, effectively means that it has 2 dimensions. two meaningful dimensions. What underlies space is energy. I don't think you can think about energy and space meaningfully without giving chance a third role that's equally as important. And by chance, I also mean fate and ultimately God. So, whereas space and energy, I fully accept, are objective, there are only two of the three. And God and fate are not. The fact that something is not objective does not mean it's not real. Things that are subjective are just as real as anything. I'll give you a couple of examples. Goodness. It would be extremely unreasonable to say that goodness is not a real thing just because it's subjective. There's no way to measure goodness and badness, but they're as real as stone and computers. So there's one example. Another example, music. There's no possible objective definition of music. There's no possible objective definition of jazz. There's no possible objective definition of musicals. Subjectivity is as important a part of our experience as this floor is. It's absolutely self-evident. My book, which proposes a definition of mind, talks about Star Trek, but it talks about them as examples of the three dimensions of personality. So transactional analysis back in the 60s put forward the idea that there were ego states that the mind transitioned between. I'm going further than that. I'm saying no, there's an inner space. So although we have an objective outer space, we also have within us a real subjective inner space. It's a mind space, not a mindset. And I'm saying that Star Trek is the perfect example to understand these three dimensions of mind, because you have three extremes to examine in their interaction and their crucial relationship to each other. You have the logical Mr. Spock, you have the emotional Dr. McCoy, and you have the pragmatic Captain Kirk. Prior to transactional analysis, we had Freudian theory, which is the same, arguably, is the same three dimensions, but with different names. And somebody quite wittily used The Simpsons to illustrate these extremes. So you have the extreme conscientiousness of Lisa, you have the extreme, for want of a better word, childishness of Homer, and you have the extreme self-knowledge, of self-awareness of Bart Simpson. On a more serious point, this could be seen as the evolution of the human mind. So the shape of the universe and the definition of mind are steps forward in our understanding of ourselves in the universe. We've got to understand both. We've got to understand ourselves better, we've got to understand the universe better, and we've got a little bit of growing up to do, and money is arguably the enemy of that. Let's go back, finally, if I can take 5 minutes. We've got a bit of time. Yeah, we've got a bit of time. Why don't I go back to the table I was talking about, and we'll just briefly talk about a frog and the final piece of the jigsaw I've tried to lay out tonight, which is that there's an apparent size to the universe. You remember from earlier that our rate of interest, i.e. the rate of expansion of the universe, was halving. So we've got one, we start off with 1, we go a half, we go a quarter, we go an eighth, a 16th, and so on and so forth. This rate of expansion is looking at it from outside the universe. We're trying to take a view of the whole universe, and we're positioning ourselves outside of it to do so, in our imagination. We're not outside the universe in reality, we're inside the universe. If we only look at the expansion outwards, it seems to us the universe is getting bigger and bigger and bigger and faster and faster and faster. But that's only because we can't see the smallness rushing towards us. I know this is a lot to get your head around, but bear with me, you'll see how this works. Because we're in the universe, we're looking at this and we're seeing 1, 2, 4, 8, 16. And the reason I say that is described here. I'm using a frog because I'm using the ideas of the philosopher Zeno, who was born 2,000 years ago. And in case you don't know, Zeno identified this paradox of a frog trying to escape from a lake, jumping half the distance to the edge each time, and somehow never managing to do it, never managing to escape. So the frog, with its first jump, jumps halfway from the centre of the lily pad to the next lily pad and can see the edge. It's only got the same distance to go again, but the frog's tired from its jump. So it thinks, well, I'm not going to make it this jump, but there's still only a couple of jumps for me to get out of here. So it jumps again, but again it's only half. So now it's jumped three quarters of the distance. The frog's still thinking, I've only got a couple of hops to get out of here. I'm a bit more tired than I was, so I might not make it this time, but jumps again, 7/8 of the way towards the edge. It's got now. But, and we all know the denouement, it doesn't matter how many jumps the frog makes, it's never going to reach the edge. We're not in that situation, but only because it isn't the frog that's jumping, it's the lily pad. And the lily pad isn't going out of the universe, it's going inwards, as we've said about this thin part of the horn. Because the movement inwards is getting less each time, this frog, which is looking at all the previous hops, because it's only able to see the edge, and so that's what it's looking at all the time, the edge of the universe. When time passes and the distance travelled halves again, as a result of time passing, then this frog suddenly sees all of these suddenly get twice as big. So the frog is seeing an exponential growth, the exponential decrease that we've got in our table. So we've got an exponential decrease, but because we're accumulating it, the exponential decrease only means that the overall expansion hits a sensible natural limit of 2 of the original unit. And what's very, very germane about this is that if we look at this point in the progression, then we see we're about halfway between 13 and 15, 13.01 as opposed to 15.01. So 14 is a little bit more than 13.8. when we look at the apparent size here, which drops out automatically from the figures we've already used, we've already agreed, what we see is that the halfway point between 64 and 128 is 96. And 96 is just a little bit more than 93, just the same as 14 is just a little bit more than 13.8. So the reason why the universe appears to be 93 billion light years wide in its size is because we're looking at it as if we were outside when in fact we're inside. That's absolutely covered all the ground, which is great because we're still well within our time. And what I will say is that I'm not a physicist. I don't know what questions to ask. I don't know how to put this in terms which a physicist would relate to from his field. All I can do is put this forward to my peers, which is the people here, and wait for physicists to take it up on their own behalf, and if they've got issues, come back to me to say, look, we think you're wrong and here's why. Because as things stand, I'm pretty much done. There's nothing, I don't really have any questions. I don't really have things that don't fit into this. I just want to leave you with that in case there are individuals who think, well, I'm afraid this is very plausible, but it's just not right because of X. Then, let me know, because I'm not aware. Okay, thanks very much for coming tonight. I hope you have enjoyed it. I have. And, well, if you can leave a review or follow up with the resources that are on the website, or even go to lulu.com and buy the print version of the book rather than downloading the free PDF, that would be great.